Hello viewers, in today's session we are going to discuss an important problem from increasing functions. So here we have this problem where we have to prove that the function f of x which is equal to 3x minus sine x is an increasing function for all x belonging to the set of real numbers, right? So before solving this problem, let us first quickly see the definition of increasing function in terms of derivative. Suppose we have a function, say y is equal to f of x, which is defined in some domain D, right? And if the derivative of this function, that is f prime of x, is greater than 0 for all x belonging to the domain, then the function y is equal to f of x is said to be an increasing function. So here if the derivative, that is dy over dx, that is the slope, is always greater than 0, or this quantity is always a positive quantity for all x belonging to D, then the function y is equal to f of x is said to be an increasing function. So here will prove this function to be an increasing function using this definition, right? So let us here find out the derivative of f of x, right? So f prime of x is given by d by dx of 3x, and then we have d by dx of sine x. Now f prime of x is equal to 3 times 1, because we can take this 3 outside this derivative operator, and the derivative of x with respect to x is 1, and the derivative of sine x is cosine x, right? So f prime of x is now equal to 3 minus cosine x. So now we have to show that this derivative is always a positive quantity for all x belonging to R. So for this we have to take help from trigonometry. So here we have cosine x, and we know that the range of cosine function is given by this interval, that is minus 1 to 1. So we can now here write cosine x greater than or equal to minus 1 but less than or equal to 1. And remember here the domain of this function is the set of all real numbers, right? So let us start with this inequality. So here we have negative cosine x. So let us multiply this inequality throughout by minus 1. So here we have plus 1, here we have minus cosine x, and here we have minus 1, and the direction of the inequality gets reversed, right? So we can also write this inequality as minus 1, and then we have minus cosine x, and then we have here plus 1, right? Okay, so here we have 3 minus cos x. So let us add 3 throughout this inequality. So we have minus 1 plus 3. Then here we have 3 minus cosine x. And here we have 1 plus 3. So 3 minus 1 is 2. And 3 minus cos x is given by the derivative, that is f prime of x. And here 3 plus 1 is 4. So from this inequality we can easily conclude that the derivative it lies in the interval, that is 2 comma 4 for all x belonging to the set of real numbers. So now from this interval we can easily conclude that the derivative f prime of x belongs to this interval, and here 2 is a positive quantity and 4 is also a positive quantity, right? So f prime of x is always going to be a positive quantity for all x belonging to R, because here 2 is positive and 4 is also positive, and the derivative is having values between these two numbers, including 2 and 4, right? So f prime of x is always a positive quantity for all x belonging to R, and from this definition now we can easily claim that the function f of x is an increasing function, because the derivative is always a positive quantity as f prime of x belongs to this interval. So f of x is an increasing function for all x belonging to R. Hello viewers, in today's session we are going to discuss another important problem from domain of functions, and here we are going to find out the domain of this function f of x, that is equal to 1 over square root of x square minus 1, and here we have sine inverse x minus 1 over 2 plus logarithm of x minus 1, right? So here we'll see how we can find out the domain of functions where we have a combination of functions. So here we have the product of these two functions, and then this function, that is the natural log of x minus 1, is added to the product of these two functions, right? So here we'll first separately find out the domain of these three functions, that is 1 over square root of x square minus 1, and then sine inverse x minus 1 over 2, and then natural log of x minus 1. And then by the concept of intersection of domains, we can easily identify the common domain or the common values of x which satisfies all these three functions simultaneously, right? So let us start. So let us first assume that this function is g of x, that is 1 over square root of x square minus 1, and let us take this function as h of x, that is sine inverse x minus 1 over 2, and let us take this function as p of x, that is natural log of x minus 1, so that we can now write this function f of x as g of x times h of x plus p of x, right? Okay, now let us assume that the domain of this function g of x is d1, the domain of this function h of x is d2, and the domain of this function as d3, right? And the domain of this function f of x as d. So the domain of this function f of x, that is d, can be written as d1 intersection d2 intersection d3. That is, we have to identify the common interval which satisfies this function, that is f of x, or the common values of x for which this function is defined, right? So let us find out the domain of the function g of x, h of x, and p of x one by one. So let us first take g of x. Now see, here in the denominator we have square root of x square minus 1, and clearly this function g of x is defined for those values of x for which x square minus 1 should be greater than 0, right? Because x square minus 1 should be a positive, because x square minus 1 is inside the square root sign, and inside the square root sign we must have a positive quantity, because the square root of positive quantities are defined in the set of real numbers. And if x square minus 1 is a negative quantity, then the square root of negative numbers are defined in the set of complex numbers. But here we are talking about the real numbers, so x square minus 1 should be greater than 0. So here we can now write this inequality as x square is greater than 1, right? And we can also write it as x square greater than 1 square. So now we have to find all the values of x which satisfies this inequality. So here we'll make use of an important result, and the result it goes like this. If we have say x square greater than a square, then the value of x belongs to this interval, that is minus infinity to minus a union, and here we have plus a to infinity, right? And if we compare this inequality with this one, then the value of a is 1, right? So the solution of this inequality is given by minus infinity to minus 1 union 1 to infinity. And let us represent these values of x on the real number line. So here we have the real number line, minus infinity, here we have plus infinity, here we have minus 1, and here we have plus 1, right? So x belongs to minus infinity to minus 1. So here we have this region, and then we have 1 to infinity. So here we have this region, right? So here minus 1 and 1 are not included, because x is equal to 1 gives us 1 square minus 1, that is 0, which can be discarded, because then the function g of x is not defined. And similarly, when x is equal to minus 1, then minus 1 square is positive 1, and 1 minus 1 is 0, and again the function g of x is not defined. So we have to discard minus 1 and 1. So the domain of this function 1 over square root of x square minus 1 is given by this region, that is from minus infinity to minus 1 and 1 to infinity. So we can now write here d1 is given by minus infinity to minus 1 union 1 to infinity. And here we have used the direct result for the solution of this inequality, that is x square greater than a square, and the solution is x belonging to minus infinity to minus a union a to infinity. So let us now find out the domain of h of x. So here we have the inverse sine function, that is sine inverse x minus 1 over 2, right? So here I will make use of the concept of inverse trigonometric function, that is the function sine inverse theta. The range of sine inverse theta belongs to this interval, that is minus pi by 2 to pi by 2, provided this theta it belongs to the interval minus 1 to 1, right? And if we compare sine inverse theta with this one, then the value of theta is given by x minus 1 over 2. So x minus 1 over 2 must belongs to this interval, that is from minus 1 to 1. So from here we can form the inequality, that is x minus 1 over 2 should be greater than or equal to minus 1 but less than or equal to plus 1. So now we have to solve this inequality. So let us multiply throughout this inequality by 2. So here we have minus 2, then we have x minus 1, and here we have 2. So now let us add 1 throughout so that we can get rid of this negative 1. So we have minus 2 plus 1, here we have x, and here we have 2 plus 1. So minus 2 plus 1 is minus 1, and here we have 2 plus 1, 3. So sine inverse x minus 1 over 2 is valid for the values of x for which x belongs to this interval, that is minus 1 to 3. So the domain of the function h of x is given by this interval, that is minus 1 to 3. And let us represent this interval on this real number line. So here we have minus 1 and here we have 3. So 3 lies somewhere here, right? So now the region that is from minus 1 to 3, where minus 1 and 3 both are included, right? So this domain can be represented like this. So here we have minus 1 to 3, and here 3 and minus 1 both are included, right? And in the first case, that is when we have found out the domain d1, then we have discarded minus 1, so we'll discard minus 1 later on. So but when we consider only sine inverse x minus 1 over 2, then the domain of sine inverse x minus 1 over 2 is from minus 1 to 3. So this reason it represents the domain of h of x. So now let us find out the domain of the function p of x, that is natural log of x minus 1. Now see, here we have natural log of x minus 1, and the valid values of x for which the natural log of x minus 1 is defined is given by x minus 1 should be greater than 0, right? So x should be greater than 1. So here x minus 1 should be a positive quantity, because the natural log of positive quantities are defined in the set of real numbers, and the log of negative quantities are defined in the set of complex numbers. So here x minus 1 should be greater than 0. So solving this inequality, we have x greater than 1. So this implies that x should belongs to this interval, that is from 1 to infinity, right? So the domain of this function, that is d3, is given by 1 to infinity, and let us represent this interval, that is 1 to infinity, on this real number line. So here we have 1 and here we have infinity, so we'll go like this, right? And remember here 1 is not included, because if x is equal to 1, then we have 1 minus 1, so natural log of 0, right? So we'll discard x is equal to plus 1. So now we have obtained the domains d1, d2 and d3, and we have represented these domains on the real number line, right? And now from this diagram we have to identify the domain of the function f of x, which is given by the intersection of these three domains, right? So let us make use of this diagram to get the common values of x for which this function f of x is defined. So here the domain d1 is from minus infinity to minus 1, and union 1 to infinity, and d2 is from minus 1 to 3, and d3 is 1 to infinity. Now from this diagram we can easily conclude that the common region is given by this one, that is from plus 1 to plus 3, right? Because this portion and this portion are common to all the three domains. So here the domain of the function f of x is given by plus 1 to 3, And remember here plus 1 cannot be taken, because here plus 1 makes x square minus 1 is equal to 0. So we can here write the domain of this function f of x as 1 to 3, but here 3 is included, right? So the common region which is identified here from the domains d1, d2, d3 is from 1 to 3, and here this interval is open from the left, that is x is equal to 1 is not included, and here it is closed from the right, that is x is equal to 3 is included. So here this region, that is plus 1 to 3, is common to these domains d1, d2 and d3. So the intersection of these three domains is given by this interval, that is from 1 to 3, and all the values of x which belongs to this interval, that is 1 to 3, it satisfies or it defines the function f of x. So here this interval can also be expressed like this, that is x is greater than 1 but less than or equal to 3. So either we can represent the domain of f of x like this, x greater than 1 but less than or equal to 3, or x belonging to this interval, that is 1 to 3, open from the left and closed from the right. Hello viewers, in today's session we are going to discuss an important problem from application of derivatives, and here we are going to discuss this problem where we have to prove that the function f of x, that is equal to 2x minus sine square x, is an increasing function for all values of x belonging to the set of real numbers. So now to prove that this function is an increasing function, let us quickly see the definition of an increasing function in terms of derivatives. Suppose we have a function, say y is equal to f of x, which is defined in some domain d, right? Now if the derivative of this function y is equal to f of x, that is f prime of x, is greater than 0 for all values of x belonging to the domain, then the function is said to be an increasing function, right? So here f of x is said to be an increasing function if the derivative, that is f prime of x, is always a positive quantity for all values of x belonging to the domain. So here f prime of x can also be written as dy over dx, right? So here we'll use this definition to prove that this function is an increasing function for all values of x belonging to R. So here we can easily see that the domain of this function is the set of all real numbers. So here the domain is R, right? Now let us differentiate this function with respect to x. So f prime of x is given by d by dx of 2x, and then we have d by dx of sine square x. Now f prime of x is given by 2 times 1. The derivative of x with respect to x is 1, and here we have the derivative of sine square x as 2 sine x, and then by chain rule the derivative of sine x is cosine x. So now we have f prime of x is equal to 2 minus 2 sine x cos x is sine 2x. So this is the double angle formula for sine 2x, because we know sine 2 theta is 2 sine theta cosine theta. So now this is the expression for the derivative of the function f of x. So now let us make use of some concept from trigonometry. Now see, sine 2 theta, sine 2 theta is always going to be greater than or equal to -1 but less than or equal to +1, right? Because we know that the range of sine function is from -1 to 1. So here we have sine 2x. Now the value of sine 2x is greater than or equal to -1 but less than or equal to +1, right? So let us use this inequality to prove that this function f of x is an increasing function. So let us multiply this inequality throughout by -1. So here we have +1 and the direction of the inequality get reversed. So here we have minus sine 2x and here we have -1, right? So now here we have 2 minus sine 2x. So to get this expression, let us add 2 throughout, right? So adding 2 throughout in this inequality, we have here 2 plus 1. Here we have 2 minus sine 2x and here we have -1 plus 2. So 2 plus 1 is 3 and here we have 2 minus sine 2x can be replaced by f prime of x, and here we have 2 minus 1 is equal to 1. So we can also write this inequality like this, that is f prime of x is greater than or equal to 1 but it is less than or equal to 3. So now from this inequality we can easily conclude that the derivative, that is f prime of x, is equal to 1 or equal to 3 and it lies in the interval that is 1 to 3 where both these endpoints are included, right? And f prime of x is always going to be positive because here the value of f prime of x lies in this interval, that is from +1 to +3 for all values of x belonging to R, right? So f prime of x is a positive quantity for all values of x belonging to the set of real numbers, because f prime of x has the value lying between 1 and 3 and both these numbers are positive, right? So we can now write here f prime of x is always greater than 0 for all x belonging to R, right? So from the definition of increasing function, f prime of x should be greater than 0 for all x belonging to the domain. So here we have proved that the derivative is always a positive quantity for all x belonging to R. Hence we can say that this function is an increasing function for all x belonging to R.